Chapter 3, Lesson 2, Advanced Algebra, looking at solving these systems algebraically. We looked at solving them graphically in the previous lesson. We're going to look at substitution and elimination, which you should have had some experience with, and then what happened. And I'm actually going to look at what happened here in the first video because you may be doing substitution or elimination and run across this, so I want to look at this first. So when solving a system algebraically, you don't always arrive at a unique solution. We talked about these different types of systems that we can have: an independent, which is one unique solution; dependent, which means you have an infinite number of solutions; and then you have the parallel lines, which are yielding no solution. So how does that going to show up algebraically? We looked at solving the equations for y and looking at the slopes, but what if they're in this form and we want to do it algebraically using substitution? Well, now watch what happens. If you're doing elimination on this one, you'll notice that when you add these two equations together, you get 0 is equal to 0. So notice the variables, both of them have been eliminated. Now, what happens in that situation? What does this mean? It doesn't mean that you've done something wrong, and it doesn't mean that there's no solution. You have to correctly interpret this. And what this means is that if the variables eliminate each other, in other words, you end up with a statement like this where you have a constant equals a constant. If this is a true statement, if what you have here is true, 0 equals 0 is true, then what that means is you're looking at a system that is dependent. In actuality, it's the same equation, it's the equation of the same line. So you have a line that's on top of a line, which means you have an infinite number of solutions. Now, I want you to take special note of how we put this mathematically. We don't just say that there's infinite number of solutions or any solutions. It has to be a very specific type of solution, and this is the mathematical notation and the way that you have to write it. It's in the set notation, and so here's what this means in English, and I'll read it across, and then I'll discuss the mathematical notation for it in just a moment. This means that you can use any ordered pair x and y's such that, or as long as, it makes this equation true. All right, so that's what I'm saying in English. You can use any ordered pair as long as you make the equation y equals 2x minus 3 true. And so that's how you say it in English. This is how you write it in math language. So you use the ordered pair notation for x, y. This vertical little line here means such that, or as long as, and then you write the equation for which it must be true. Now all they did here was take one of these two equations up here in the system, solve it for y so it's in slope-intercept form, and then write your answer in this method. So if you're doing substitution or elimination and you end up with a true statement where there aren't any variables left, then you're looking at parallel lines, and this is how you would indicate the solution. Now, what happens if you're doing elimination or substitution and you end up with a statement that's not true? What does that mean? What's the interpretation there? Well, what you have here are two lines that never intersect. You're actually looking at parallel lines. So that means they're never going to intersect, which means you're not going to have a system or a solution to this system. So this would be a system that has no solution. So two scenarios to remember. What happened to my equation? What happens when I end up with a true statement? That means you're looking at a dependent solution, a line on top of a line. This is the mathematical way to represent it. If you end up with a not true statement, that means there is no solution, which means you're actually looking at parallel lines.